Hello everybody and welcome to our Systems of Linear Equations series. The first topic we're going to cover is developing systems. A system of linear equations occurs when two or more linear relations relate to the same situation. We're going to focus on just two linear relations at a time. Visually, this means there is more than one linear relation graphed at one time. So how that can look, if I give myself a coordinate plane real quick, simply that we have more than one line on the same piece. So that's how one could look. You can have two or more, so we could have 3 or 4 or 5 lines. We're just going to look at 2 lines. A solution to a linear system occurs when there is a point that satisfies both equations. Visually, the solution occurs when the lines cross. But once again, just give me a second to draw my axes. What's going to happen here is that the solution to the system is always where the lines cross. So visually, it's right there. Eventually, we're going to work algebraically. We'll just solve for that point, and we'll know that is the intersection point. There are 3 phases to working with a system of linear equations. The first phase is develop the equations of the system. The second phase is to solve the system, and there's going to be 3 different methods we're going to look at: graphing, then 2 algebraic ones, one called substitution, one called elimination, and then checking the solution. We're going to focus on the first step and the third step in this video. We'll focus on developing the equation and then checking the solutions. And then the subsequent videos will all deal with solving the equation, or solving the system in different ways. All right, so let's look at checking the solution. So if you've checked a linear equation before, this is the same thing. You'll see here I have 2 equations, so I'm just going to label them 1 and 2. By the way, a system can be, you're dealing with a system a couple different ways. Often they're just stacked like they are in this example. The other way is you'll see some brackets, some wiggly brackets. You just that shows that they're a group. So there's different ways to show this depending on what type of textbook or author you're looking at. In my video here, I'm just going to use the stacked method, but I also like the bracket method. It's a nice visual or reminder that they're together. Anyway, back to checking the solution. All I'll do is one at a time, plug these variables in, and I'm going to see if my left side equals the right side. So if that's the case, just like with any linear equation, what that means is that point belongs on that line. And we're looking for a point that belongs to both lines. So I want this point to check out with both of these equations. So C equals 2D plus 2. So C is 4 equals 2 times whatever the D value is plus 2, and the D value is 1. I just made that blue so it stands out a little bit. 4 equals now 2 plus 2. 4 equals 4. So that means this point works with this line, or it sits on that line. So graphically, if I was to draw a picture, this point would be on that line. Let's check this second line now. Because again, if it's a solution, it has to work or sit on both points at once, because it has to be that point of intersection. So C plus 2D equals negative 6. All right, C is 4 like we said, plus 2 times my D value equals negative 6, and D was 1, and now I'll just crunch the numbers real quick. So 4 remains unchanged plus 2 equals negative 6. 6 equals negative 6. That is false. 6 is not equivalent or the same as negative 6, which means this point does not sit on this line. So just a quick example, this won't represent this situation. I'm just going to make up a version that would be similar to this. It's like saying, and maybe there is a solution, but the solution that I'm testing here maybe sits on just this one line, but not on both. So we're looking for a point that sits on both lines at the same time, meaning we're looking for something that would be right here. But this one did not check out, so not a solution. Let's check B. So again, here's my first equation, second equation. I might as well stick with blue now. So my first equation, C equals 2D plus 2. That's going to remain the same. So now I'll flip to red to make another color. C is now negative 2 equals 2 times my d value plus 2. My d value is -2. And then now I'm going to crunch the numbers. -2 equals -4 plus 2. Left side -2 is fine. And on the right side, -4 plus 2 is -2. So it checks out with that first line again. So that point does sit on that line. Let's see if it sits on the second line. C plus 2d equals -6. C is -2 plus 2 brackets equals -6. Sorry guys, I'm just jumping ahead there. This is now -2. So again, crunch the numbers. -2 remains unchanged. Here would be -4 and equals -6. Subtract -2 subtract 4 more is -6. So it does sit on that line. So again, an example here, and this is not the graph that represents this specific situation. I'm just drawing something really quickly that'd be similar. So we could just pretend that this was maybe line 1 and this is line 2. We found a point that's lying on both of them at the same time, meaning that's that intersection point. That's the only possible spot where this one point could be sitting on both lines at one time. All right. Developing the system. The equations within a linear system are created by examining the details of a situation. So in these examples, I'm going to present you with some situations, and we'll have to create these two equations based on these details. So a theater stage is rectangular. Its perimeter is 158 feet. The width of the stage is 31 feet less than the length. So the first thing we'll have to do is we need to come up with some variables to represent these unknown quantities. What we're looking for in this question, I didn't word it so great here, is that the unknown quantities are the width and the length. You can use whatever you want for length and W for width. But if you want to use X and Y, you absolutely could. All right. Now, in general, there's no really set pattern to how you come up with these equations. You just look for some details in the question. So it says here, it's got a perimeter of 158 feet, and I notice it said rectangular. So right there, in my mind, I can create something out of that. That's a math fact for me. Rectangular shapes have a, rectangular shapes have a formula for their perimeter. The perimeter is equal to 2 times the length plus 2 times the width. And I know the perimeter is 158, so the first equation I come up with would be 2L plus 2W equals 158. So I can use that as one of my linear equations. So I've got one down. The next sentence says the width of the stage is 31 feet less than the length. So I can create a statement out of that as well. Now, when you do this, I like to work backwards from the thing I'm talking about. So it says length here. Whoops, I put an X here. I should put an L because that's what we're using for this, L and W. If I know that length is L, and it's saying that something is 31 feet less than the length, so I would know. I gotta switch my colors up here, sorry. My third step, which is more of a detailed kind of equation. So we have L, and sometimes you have to kind of scribble it out, and then you can kind of rearrange your equation to make it look nice after. But we have L, and it's saying that something is 31 feet less than that, so that'd be L minus 31. And what is that thing? If I keep reading backwards, and again, I'm reading backwards from the L, and I've already got the 31 feet less, so the width of the stage is 31 feet less than the length. So I'm saying is equal to the width. And that, I don't have to rearrange that one. I could if I wanted to. There's also just different arrangements or different ways I could have thought of that. I know sometimes I've had students that tell me the way they like to look at it is the length minus the width equals 31. And that's great too. So there's other ways you can think of equations. So just because you wrote an equation one way and your buddy wrote it differently doesn't necessarily mean there that one of you are wrong. You might have wrote equivalent equations and you just rearranged them differently. So one thing you can try to do is see if you could rearrange your equation to look like his or vice versa. So I guess to summarize that, I could just write down my system right here. So 2L plus 2W equals 158. And then L minus 31 equals the width. And that's the system for this situation. B says Sebi has determined that the stage is 55 feet long and 24 feet wide. Use the linear system from part A to verify that he is correct. Okay, so all we're trying to do is just check. So the length is 55 and the width is 24. And we're just going to see if these values work with these lines, these equations. So my first one, just writing that out, put my values in, 55, 24, so that's 110. This is 48 equals 158. 158 equals 158. So those values definitely work with the first equation. Now in the second one, L minus 31 equals the width. So the L is 55, the width is 24. 55 minus 30 is 25, minus one more is 24. So yeah, 24 does equal 24. So I've confirmed these values with both equations, meaning this is the correct solution. So again, that's how you would check. We've skipped how to actually figure those values out, but we will do that in the next future videos. Next future videos is a strange choice of phrase, so just in the future videos. All right, let's try one more. So 8 passenger vans and 6 passenger vans carried 110 people. There were 15 vans in all. Now to determine the unknowns, I should have added this into these questions, just how many of each type of van were there? So that's what I'm really being asked. And then when you realize what you're being asked, that's what you can base your variables on. So in the variables, they're asking, well, how many of each type of van? So I can say X is one type of van and Y is the other type of van. So I can say X is the 8 passenger and Y can be the 6 passenger. And by all means, you could have used different variables. We could have used E's for 8 and S's for 6. Whatever you want. I know lots of students like just keeping it with X and Y, and that is fine with me as well. All right, so now we've got to come up with these equations. And often it depends, I guess, the situation. And like I said before, there isn't really a pattern to find these two equations. You just kind of have to look at the situation, see what you can pull out. But oftentimes there's one like kind of basic and one more detailed. So I guess there's something you can look for, but that doesn't hold true for every single example. Anyway, let's focus back in. It says 8 passenger vans and 6 passenger vans carried 110 people. Okay, so we know that 8 passenger vans and these 6 passenger vans. Okay, so we could say X plus Y equals 110. Now, oh, I'm sorry, I read the wrong thing there. That's not 110. It should equal 15. And that's a common mistake I just made. I'm looking back here. There were 15 vans in total. So if I take X, the 8 passenger vans, and Y, the 6 passenger vans, that'd be all the vans we have. That means there should be 15 of them. So that would be one of my equations. Now for the second equation, you have to actually put in we're talking about people in the second equation. So we have to account for people in these vans. So not just X, but it would be 8X because there's 8 people for every one 8 passenger van. Plus 6Y because there's 6 people for every one 6 passenger van. And that's going to equal all the people. So once you count up all the people in their vans, that would add up to our total amount of people, which is 110. So there's my second equation. This is the hardest thing, I think, in this unit, is coming up with these equations. Some of the techniques we use to solve can look difficult, but they're, well, there's a procedure to them. So they're step by step, and you can just kind of follow the procedure to get an answer. Coming up with these equations just takes some of your own logic, so that can be tough. Anyway, to summarize, I can just write this out, and it wouldn't matter which equation I write on top, if in case you're wondering. But yeah, so I'll just write these out. And again, if you want to put the bracket to show that they're grouped, that they're a system, by all means, go for it. In D, we could just check this, but I'm going to kind of skip that part because I'm sure you guys have that down by now. But if you don't, you can always come talk to me. I just want to save you a little bit of time on this video. I want to do one more after thinking about it, one more example. And I wanted to put something in here with values. So if you look at this example, it says a school raised $140 by collecting 2,000 cans and glass bottles for recycling. The school receives 5 cents for a can and 10 cents for a bottle. There's more detail in this question. Now, what they're going to be wondering about, again, I didn't write this in my example and I should have, is how many bottles and how many cans did they collect? So once I know that, then in my variable stage, I know that's how many bottles and okay. Now step 2, equation. There's going to be more than one. So a school raised $140 by collecting 2,000 cans and glass bottles for recycling. The school received 5 cents for a can and 10 cents for a bottle. Okay. Well, how would you come up with the $140? Well, I guess you'd add up your cans and your bottles. But it's not just adding the cans and the bottles, you'd add up their value. So how much would the recycling company give you for each? And it says over here you get 5 cents for a can and 10 cents for a bottle. So I actually have to factor that in with my 140. So your numbers do tie together. I'm using my money numbers together, my $140 and then the cents. So I'm using all those money numbers together. So for a can, 5 cents per can, so 0.05 per can, plus my 10 cents for a bottle. When I add all those individual monies up, I'd get my $140. So I take the money I got for recycling my cans, which would be 5 cents times the number of cans, and then 10 cents for the number of times the number of bottles. Now, as I'm writing that, I should fix up my variables. I was kind of lazy. It's not just bottles, it would be the number of bottles, and this would be the number of cans. So that is something I'm bad at. I'm sometimes lazy with my descriptions and my variables, but really I shouldn't be. I got to be descriptive. B represents the number of bottles. So in my expression, then I know it's 0.10 times B means 10 cents times the number of bottles. Okay, so that's my first equation. My second equation. Now they just tell me the sheer number of items. I have 2,000 items, and those items are bottles and cans. So that's a nice basic one. I can just go, I wrote C first, so I might as well do that again. C plus B equals 2,000. So if I just count up how many things I have, I'm gonna have 2,000 things, and there's only two types of things, cans and bottles. By the way, if you would have put B, then C, that'd have been fine. Same within the first equation. If I would have put 0.10B first, that'd have been fine. All right. I just, again, to save time, I won't write out those two equations again. You can see they're right there. Also, I'm not going to check it because I think you know how to check it. Instead, let's look at one more situation. Okay, school sold 175 smoothies to raise money for a charity. A banana smoothie costs $3 and a peach mango smoothie costs $5. The school raised $625. What we're wondering in this question is just how many of each type of smoothie did they sell? Okay, so there you can go X and Y, it's up to you. You could go B and P if you want though. So I'll go B for number of banana smoothies. Sorry, I'm writing slow, everybody. And then P, number of peach mango smoothies. Okay, now whenever you're involving money or values, you can also use a little chart to help you. But we're going to go over that chart in a future lesson. So let's look at equations now. So something we talked about before, let's use like similar types of numbers should go together. So in this one, I see that there's a bunch of money numbers in here. So we know they're going to go together. So banana smoothie costs $3 and a peach mango costs $5, and then we know we raised $625. Okay, so we'd have to add up the amount of banana smoothies we sold and then times them by the value, because that would be how much we raised. So what I'm trying to say is that I'd write 3B to represent how much money I made off just banana smoothies. It's $3 per smoothie. And so it'd be 3 times B. B means the number of banana smoothies I sold, plus 5P, because it's $5 for every peach smoothie I sell. And if I add up the values or the money I made from the banana smoothies and the peach mango smoothies, I'd get $625. So I've used all my money numbers up to create that equation. The next one, I just see I have 175 smoothies to raise, or sorry, smoothies to sell, or I sold 175 smoothies. So that means if I just add up the individual smoothies, I'd get to 175. And there's only 2 types of smoothies, so B plus P equals 175. Again, B represents the number of banana smoothies I sold. So if I add those up, it should equal 175. So that would be my second equation. And again, it's kind of following that little bit of a guideline you can have where often you have one basic equation. So I'd call that my basic one. And then one more detailed one. So sometimes there's that pattern you can look at, but that pattern doesn't hold for every question. But you will maybe notice that you see it. Okay, that is everything that I was going to look at in this first video. So we learned how to, what a linear system was, how to check the solution, and then how to develop the initial system. What we'll look at in the next videos is how to actually solve and come up with them. Meaning, in this example, example 3, how did they come up with 125 as an answer, and how did they come up with 50 as an answer? Until then, have a great time working on this stuff.